Hello, everyone. Today we are going to talk about preliminaries. These are the topics of today's class. Some of you who have some experience on AI might know these stuffs. And if that is the case, please think of it as a recap. And for those of you, this class is your first AI experience, then these are going to be some preliminaries that are necessary to understand the following classes. So first of all, we're going to talk about types of learning. And then we're going to talk about the overall workflow of developing AI models. And then we are going to take a deeper look at each component of the workflow. And then we're going to discuss some linear algebra things and then NumPy. Many people say that linear algebra is essential for developing AI or understanding AI technologies. And we're going to have a look at why this is so. And then we're going to discuss some functionalities of NumPy. NumPy is a very famous Python library that helps perform numerous linear algebra operations. And then finally, I'm going to summarize this lecture. Okay, first of all, types of learning. So, what are some of the types of learning? The first thing is supervised learning. As you can see the eye here, we have access to some labels to our data. And unsupervised learning, we do not have any labels. And we are not supervising these data. So the eye is blocked. And the third type of learning is called reinforcement learning. In the case of supervised learning, the aim of supervised learning is to learn a function that maps an input data X to an output Y. And the examples include classification, translation, and captioning. In the case of classification, for example, let's say we're given a set of pictures of dogs or cats or what else, plants. Then when we are given feeding this image to our function, then we want our function to output the label dog. And when we input these plant pictures to our function, then we want our function to produce the plant label. So in the case of supervised learning, what we want our function to produce is determined, and we call that output labels. And in the case of translation, what we want to do is when we feed, let's say, Korean sentences, then we want our function to output a German translated sentences or English translated sentences like this. And in the case of captioning, we feed an image, and we want the caption or the explanation or description of the image. And in the case of unsupervised learning, we want to learn a function as well. However, in this case, we do not have labels, and we're just given the data. So in the case of supervised learning, we are given a pair of data, like a dog image, and then the label dog. And the second data consists of plant image, and then the label plant, like this. However, in the case of unsupervised learning, we're just given the images. For example, we are not given these labels in the case of unsupervised learning. However, still, we want to learn a function, and we want to learn something called a distribution function. And what these unsupervised learning algorithms are doing is analyzing the distribution of input data. So how images are distributed and how they are constructed like that. And examples of unsupervised learning include clustering, factorization, kernel estimation, and etc. And in the case of reinforcement learning, we also want to learn a function that maximizes the long-term reward R. So here we have an agent, and this agent takes some actions. And this environment changes its state. And then this agent can observe the state or state variation or observation. And it also receives reward from this environment. And through reinforcement learning, it learns a function that which actions might maximize the long-term reward. Here, this long-term is very important. We are not focusing on short-term reward. Let's say an agent can take two paths like this to reach the goal. The first one gives +1 rewards on the way. However, the second path gives -2 reward at the beginning. And because this one is shorter, and let's say there is water here, and because this is slippery, it gets -2 reward. However, this path, the first path, is just a plain path. So you're just receiving +1 reward on the way. However, in the second case, you're receiving -2 reward at the first step. However, this one is shorter, so you are going to receive 10 reward. And if this agent wants to maximize the reward in every step, then it's going to take the first step because it's +1 at the beginning. However, the second path is -2. However, this is not what we want. What we want is maximizing the long-term reward. So even though in the short term, we could get some minus rewards, but in the long run, we're getting +8 reward if we are taking the second step or second path, then this agent is going to take this second path rather than the first path. Okay, so here, long term is very important. And examples of reinforcement learning include games, a lot of games in Go, chess, self-driving cars. So here, in all three cases, we try to learn function, but different types of functions. And nowadays, we have generative models and self-supervised learning paradigms. And because of these two paradigms, the line between supervised learning and unsupervised learning is becoming a lot blurry. And we're going to talk about these generative models and self-supervised learning algorithms in the following lectures. And in this course, we're going to cover a set of representative supervised learning and unsupervised learning methods. And if time permits, we're going to discuss some fundamental reinforcement learning algorithms. However, reinforcement learning itself is a big area, so you need at least 2 semesters to discuss reinforcement learning in details. All right, from now on, I'm going to give you some concrete examples of supervised learning, unsupervised learning, and reinforcement learning. One example of supervised learning is regression. In Korean, it's called 회귀. I told you that all three paradigms, supervised learning, unsupervised learning, and reinforcement learning, try to learn a function. And in the case of supervised learning, this function tries to map an input to an output. And in the case of unsupervised learning, this function tries to analyze the distribution of the input. And in the case of reinforcement learning, this function is to determine which actions to take to maximize the long-term reward. So what is the mapping is going to be in the case of regression. In the case of regression, the mapping is going to be a set of real numbers, like n real numbers, to a single real number. So for example, let's say we want to analyze the stock market, and we are given a record of 10 days. This is Chinese character, 10 days of history. And from this 10 days of history, we want to predict the stock price of the next day. And it's going to be one number. So we are constructing data like this. So day 1, day 10. So we are given like the stock price of the first day, stock price of the second day, and stock price of the 10th day. And we want to predict the stock price at the 11th day. And we are going to gather a lot of these data and train our model and possibly predict the stock price in a correct way. So this is one example of regression. Here, what we want to predict is a single real number. And another example is, let's say we have some features like this X represents the amount of time we work out, and Y represent the muscles built. And we want to predict if we work out like 10 hours, then how much muscles are going to be built. We want to predict that kind of thing. And this one is also one case of regression. Okay. And another example of supervised learning is ordinal regression. Ordinal regression is also called ordinal classification or ranking. And these two concepts are slightly different. I'm going to discuss what are the differences in the following slide. However, as the name suggests, what we want to predict is the order rather than a specific number. Okay? And let's contrast these two concepts. In the case of ranking, what we want to do is just predict the correct order. That is all we want to do. So let's say we have 3 movies and we want to classify or predict the right order of preference. So I love this movie the most, and the second movie is this one, and the third movie is this one. However, in the case of ordinal regression, what we want to do is we want to predict the correct label, but this label should be correctly ordered. So in the case of ranking, you're just predicting the order. However, in the case of ordinal regression, we're doing extra job. We want to predict the order as well as a specific label or some numbers. So we are doing 2 jobs in the case of ordinal regression. And in the case of ranking, we want to just predict the order. So in the case of ranking, if the order is correct, then there is going to be no loss. However, in the case of ordinal regression, we need to be correct in both ordering and labeling. And in the case of classification, so in the previous case, regression, we need to predict some numbers, correct numbers. However, in the case of classification, we need to predict the labels. So let's say we are given some number, then we want to classify that number into minus label or plus label. And there might be a boundary between these two data, these two groups. And we want to find this line through our learning algorithms. So that is one example of supervised learning. And I want you to differentiate these three concepts. So let's say there are only two labels, dog or not dog. And as the name suggests, binary, there are only two labels or two classes. And among these two classes, we want to choose the correct one. So in this case, because this picture contains a dog, the label should be dog rather than not dog. Okay, that is binary classification. We have two classes. And in the case of multi-class classification, as the name suggests, we have multiple classes, dog, cat, bus, plant, like this. And we want to choose the correct label among these multiple choices. Okay? However, sometimes this picture contains two objects, plant and dog. So these two options are viable. So here comes multi-label classification. As the name suggests, we have multiple choices like dog, cat, bus, and plant. And we want to choose multiple labels rather than just one label. So in the case of binary classification, we have two options. And among these two options, we choose one choice. We make one choice. And in the class of multi-class classification, let's say we have n options. And among these n options, we want to choose one of them. So we are making one decision, one choice. And in the case of multi-labeled classification, we have n options. And among these n options, we're going to choose m choices. So these are the differences between binary, multi-class, and multi-label classification. Okay, up to this point, we discussed some examples of supervised learning. And from now on, I'm going to give you some examples of unsupervised learning. Unsupervised learning is sometimes called representation learning or dimensionality reduction, because in most cases, we use unsupervised learning to reduce the dimension of the input data. So let's say, in fact, we don't use labels, but let's say we have two categories of data, and PCA tries to maximize the variance of the whole set. So after we reduce the dimension, the variance between the variance of the whole data becomes maximized. And in the case of LDA, the distance between groups becomes maximized. So 2D data is projected to this 1D line. And if you just check this point, then we can easily classify these two data groups. And why we try to reduce the dimension? Because high dimension data are very hard to deal with because they are computationally complicated and it's hard to visualize and etc. So there are many reasons to reduce the dimension. Okay, so this is unsupervised learning, one of unsupervised learning. And there is something called autoencoder. Let's say we're given an image, and this autoencoder reduces the dimension. Let's say the dimension of the input image is 3 by 244 by 244. And this encoder reduces this data into, let's say, 1000 dimension vector. And this becomes compressed quite a lot. And using this 1000 dimensional vector, this decoder reconstructs the input data. And if we compare this data, reconstructed image with the input image, so we're comparing these two entities, then even though we do not feed any labels, we can train this autoencoder. And by using autoencoder, we can reduce the dimension of the input drastically. And when we need to, let's say we need to store like 1 billion images, then rather than storing these 3 by 244 by 244 billions of these images, if our autoencoder can store this 1000 dimension vectors, then we can save a lot of memory spaces, because we can reconstruct the original image from these latent vectors or compressed vectors. So this one is another example of unsupervised learning. And another famous algorithm of unsupervised learning is clustering. We want to assign group membership to unlabeled examples. So when we visualize some data, then we can group some data because they have similar features like this. And a systematic way of doing so is clustering. So rather than just visualize some data and manually cluster or group some data by ourselves, there are some systematic ways to cluster unlabeled data so that data groups having similar features are grouped in the same group. And the last type of learning is reinforcement learning. And I told you that our agent is trying to maximize the long-term reward. So our agent is interacting with the environment by taking some actions, and our environment gives reward to this agent, and this agent can observe the states of this environment. And through a lot of interaction, so here, interaction is very important. So this agent interacts with this environment, and by interacting for enough time, this agent learns that in certain situations, it knows which actions to take. And StarCraft is one of the most famous examples of reinforcement learning. And observations can be various features like non-spatial features or screenshot features or minimap features like this. Okay, up to this point, we discussed the types of learning. And I want you to solve this problem to check your understanding. Please pause the video and take some time and solve this problem. And then please move on. Okay, have you guys solved this problem? Let's check the answer together. The answer is training autoencoders demands labels for training. I told you that we do not need any labels because we can feed the same image as inputs as well as outputs. So we don't need any labels. And regression requires labels for training. In the case of stock price prediction, I told you that we need to provide some labels. So let's say day 1 price to day 10 price, and day 11 price of day 11 is going to be the label. And unsupervised learning is often referred to as representation learning. We are learning compact or reduced dimensional data representation using unsupervised learning. And I told you that reinforcement learning aims to maximize the long-term reward, even if it would sacrifice the short-term reward. I gave this example. So there is slippery water at the beginning, +1, +1, +1, +1, and +10. Then even though it sacrifices the short-term reward, because at the first step, it's going to take -2 reward. If it is going to take the second path, it still is going to take the second path because it's going to maximize the long-term reward, which is +8. In the case of the first path, it's going to be +4. Okay. All right, that was about types of learning. And from now on, we are going to talk about the overall process of developing an AI model. In all cases of machine learning or deep learning, we need to have data to develop our models. So we first need to get data ready. That is our very first step. And after that, what we want to do is we surely need to build or pick a pre-trained model according to our problem. Because many researchers actively developed various types of models, we can choose or pick one of them. However, in your specific problem, there might not be any models that suit your problem domain. In those cases, you need to build your own model or modify the pre-trained or pre-existing models. In any cases, you need to pick a proper loss function and you need to choose the right optimizer. However, in certain cases, you need to design your own loss function or your own optimizer. And after that, you build a training loop and you are going to train your model. Sometimes it is called learning a model or training a model. Both terms are used nowadays, so don't be confused. And after we build our model and then design our training process like this, then of course, we need to fit the model to the data and make a prediction. So we use another term, fit, learn, training, fit a model, all refer to the same concept. So we're going to fit the model to the data and make a prediction. And after that, we need to evaluate how good our model is. If our model is very good, then we are going to stop our training process and then we're going to use that model for our application. However, in most cases, the first training process is not successful. Before we develop our model, there might be our goal performance. And we need to achieve this performance before we stop training or developing our model. So we need to evaluate our model, and if it does not satisfy the goal performance, then we need to improve the performance through experimentation. And this fifth step usually means going back to the first or second or third steps and then redo those steps. Then we can improve the performance. So this process is like iterative process. We go back to the previous steps and then redesign or recollect data. And finally, if we attain the goal performance, then we are going to stop. And when that happens, we are going to save and use our model for our application. So this is the overall process. All right, and now let's talk about each step in more detail. I told you that we need to prepare data. And more specifically, we need to prepare 3 types of data sets. And because we are students, let's talk about our cases. We usually study some topic through course materials. And after that, to check our understanding, we take some practice exams. And through these practice exams, we sometimes go back to our course materials and then deepen our understanding of the subject or the course. And after we go back and forth these 2 processes, studying the course materials and taking some practice exams or practice problems, then we finally take the final exam. And we want to do very well on this final exam. Even though we are good at practice exam, but not good at final exam, then that means nothing. What we really want to do is getting high score on final exam, because that's going to determine our grade. And machine learning does pretty much the same thing. In the case of machine learning, we say the course materials are training sets. So these training sets, our models learn some useful patterns. So model learns patterns from here. And through validation set, it checks whether the training process is going in the correct way or desirable way or not. And after all, we take the final exam, and this is called test set. And see if the model is ready for the wild. So even though our model is very good at practice exam or validation set, if it is not good at test set, then we cannot use that model for our application. And here comes a very important concept, generalization. This refers to the ability for a machine learning model to perform well on data it hasn't seen before. The final exam will not include the identical problems in the practice exam. Final exams are going to contain new problems. And our model, AI model, needs to do the same thing. It should be able to perform well on data it hasn't seen before. So new data, okay? So that was first step, collecting data, and we need to collect 3 types of data. The first one was training set, the second one was validation set, and the third one was test set. And after we collect data, what we want to do is building an efficient model. And there are various models already. For example, random forest, naive Bayes, nearest neighbor, support vector machine, neural networks, and etc. Many more. And you can choose one from them according to your data structure and type. And in the era of deep learning, we usually use neural networks rather than other algorithms. However, you need to keep this in mind. Deep learning has become feasible or possible because of these two things. First thing is the availability of big data. Before 2012, there were not many big data sets. However, after 2012, we now have access to big data. And the second thing we need to secure for deep learning is computational resources. If we do not have access to computational resources, then we cannot process big data. After 2012, these two requirements were met so that deep learning could surge. And that means if you do not have big data or GPU, computational resources, then we cannot apply deep learning methods to our applications. So for example, embedded systems, we do not have access to high computational resources. In such a case, traditional machine learning algorithms like random forest, naive Bayes, nearest neighbor, support vector machine are going to perform better than deep learning algorithms. So you should not blindly choose deep learning algorithms, but you need to think about your computational resources like this and how much data you have. You need to consider these two conditions. Okay. However, in this course, we are going to focus on deep learning, and we're going to discuss what neural networks are. The anatomy of neural networks are like this. We have input layers. Data goes in here, and we have 3 units. Let's say this is the height, this is the weight, and this is the age. And this hidden layer learns pattern in data. So we have 3 units in the input layer, and that means the input data has dimension of 3. Okay. And using this hidden layer, we learn patterns in the data. And this output layer, in the case of unsupervised learning, it outputs learned representation. Or in the case of supervised learning, it outputs prediction probabilities. So it's like diabetes or not, like this. And one thing to note here is that each layer is usually a combination of linear or nonlinear functions. I'm going to discuss this in more detail in the following slide. And the second thing is, I use the term patterns quite a lot. However, this term is quite arbitrary. You often hear embeddings, weights, feature representation, feature vectors. And all these refer to the similar concept. So don't be confused. They are similar things. And the third thing is, we say this network is a 2-layer neural network because we do not count this input layer, but these two layers. So 3-layer neural networks look like this. So we have 2 hidden layers and 1 output layer. So in total, it is a 3-layer neural network. And I told you that each layer is a combination of nonlinear and linear functions. And why do we care about nonlinearity? First of all, let's represent a 2-layer neural network mathematically. This is the input. So X is the input of RD. And in the previous slide, this node has 4 connections because the hidden layer has 4 units. And the second unit also has 4 connections. And this one has also 4 connections. So the input has dimension of 3, but it has 4 connections. So we need 3 times 4 numbers to get 4 units of hidden layer. So X, the input, has dimension of D, and W1 has dimension of H by D. So after we multiply W1 and X, it's going to become H times D, say D times 1. And these dimensions reduced. And this one is going to be H by 1 dimension, as in this picture. If you don't understand this part, don't worry too much. I'm going to discuss this concept in the following lectures. And after that, we pass through this max function and then multiply another matrix, W sub 2. And here, the function max is called the activation function or the nonlinearity. And what if we try to build a neural network without this max function? Think about it for a moment. Pause the video. And then we'll discuss it together. Okay, have you thought about it? So if we remove max, then our f is going to be w2 dot w1 dot x. However, this is equivalent to w3 dot x, where w3 has this form. And we cannot distinguish these two functions. They're identical, meaning that we end up with a linear classifier again. Therefore, even though we stack like, let's say 1,000 linear layers, it is just equivalent to a single linear layer. So that is why we need to have this nonlinear function to keep the complexity. And why do you want to make this function complex? Because complex functions can model complex data. So if our data is very complicated, then we need to employ complicated functions to deal with complicated data. And another reason is nonlinear functions map features into linearly separable space. What does it mean? Pictorially, let's say we have this kind of data, the circles. And it is quite hard to design a decision boundary between these two. However, If we map this data in Cartesian coordinate into polar coordinate, then we can separate these two groups using a simple linear line like this. And because we can use this simple line, our model could become efficient and effective as well. That's why we use nonlinear functions. And there are numerous types of activation functions or nonlinear functions we can choose from. And ReLU, this one, is a good default choice for most problems. However, according to your application, sometimes ReLU might not work as you expected. In such a case, you need to choose your own activation function or design your own. Okay, that was the second step. And from now on, we are going to talk about the third step, training our model. In the beginning of this class, I told you that in all three cases, supervised learning, unsupervised learning, and reinforcement learning, what we want to do is learning a function. And we want to learn the function from our data. And that is why we sometimes call this process as statistical machine learning. And how are we going to train our model? We first need to have some goals. By the way, our function could be in any form, but let's say our function looks like this. Then here, these A and B are parameters. So here, the parameters are represented as theta, or we can use more complicated function like this. And these three numbers are going to be our model parameters. And we need to choose the correct or proper parameters to deal with this input X. And how can you choose these parameters? And training our model means selecting a good parameters. And in the second step, which was building this neural network, was determining this function architecture. And after we build our model, we need to choose or find the set of parameters that will work for our application. And to do so, we first need to have a goal. And this goal is called objective function. For example, in the case of dog classification, the objective is correctly classify dog or non-dog. And what we want to do is we first pass our input, this dog image, into our function. And the output, y prime, is going to be sometimes similar to our y or sometimes different to our y. And we're going to compare these two results, the output of the function and the true label. And we want to reduce the gap between these two. And that is called minimizing the loss. So loss is the distance between these two numbers or these two entities. And we want to reduce the gap between y and y prime. So we need to find theta, the model parameters that minimize the loss, the true label, and the function output, which is y prime. And this process is often called optimization. And there are various types of loss functions for different tasks. For example, mean squared error or mean absolute error, cross entropy, negative log likelihood, connectionist temporal classification, and etc. And for more details on loss functions, you can refer to this link. Then, how do we optimize our models? For example, we want to find x that minimizes this function. It's pretty straightforward. When x equals 1, we have one global minimum, because we can vectorize this one as this. This looks like this. And here we have the minimum value. Why do we have just one global minimum? Because this function is convex. However, in real world, the loss function is quite complicated and non-convex. Meaning there are going to be many local minima, no analytic solution like this. So there are many minimums, minimas, looks very complicated. So rather than taking an analytical approach, what we are going to do is taking a numerical method. We're going to iteratively find a better set of parameters. And one of the ways to do so is using gradient descent. We update the parameters theta based on the training data. However, you need to keep it, so let's say this is the parameter space, and we are rolling this ball using gradient descent and tries to find the set of parameters that minimizes the loss. And we are using the entire data to update these parameters for a single step. And using entire data can be time consuming because we are using big data. So we don't usually do this. We update parameters based on a subset of training data. So here, this input is not the entire data, but a subset or a mini batch of the entire data. So why do we use stochastic gradient descent? In general, the training data is too big. I told you that we're using big data. And we cannot fit the entire data in our computer memory. On the first hand, it is impossible. And it takes too long to calculate the gradients using the whole data set. And sometimes smaller batch size helps avoid suboptimal minimum. In fact, using batch-sized data for each update leads to better performance. And modern deep learning is founded on SGD, stochastic gradient descent. So, to recap, what we do is take forward path. So we feed our data and then get the results and compare this result with the label. And this is called loss calculation. And using this loss, we are going to backpropagate the loss and adjust the weights or parameters to reduce this loss. So we are taking 3 steps: forward step, loss calculation, and backpropagation to find a better set of parameters. All right, and then we need to evaluate our models because we cannot train our model forever. So how do we know when to stop SGD? We cannot optimize our model forever. I told you this. And we're going to use the value. We could use the value of our loss function, but this loss function is not very intuitive and hard to tell which value is appropriate. So what we do is we use some evaluation methods. And we use some famous metrics like accuracy, precision, recall, F1 score, or confusion matrix. We use these types of metrics to evaluate our model. So this loss function is for computer. However, these metrics are for humans. And after we evaluate our model, if the performance is not satisfactory, what we are going to do is improving the performance. And we are going to utilize our training and validation data sets for analyzing performance. And there are two cases. The first case is overfitting and the second case is underfitting. I'll show you the picture. In the case of underfitting, the training loss and test loss, they both are very low. Meaning you need to study more. You haven't studied enough. Our study need to study more. And in the case of overfitting, the train loss is very low. However, the test loss is quite high. So you just memorize the practice exam, and it does not generalize to train a test set. And this is the ideal case. The train and test losses are similar, and both are low. So in the case of underfitting, train and test losses are similar. However, they are quite high. And in the ideal case, both are similar, but at the same time, they are low. And how do you deal with overfitting? In some cases, overfitting occurs because we do not have enough data. And one of the straightforward ways to tackle overfitting in that case is just preparing more data. That's very simple. However, sometimes getting more data could be very expensive. In such a case, we are going to augment our data. So augmentation is like this. Let's say we have an image, and we're going to make this two instances. The original one, and in the second case, we're going to adjust the brightness or rotate this image. So this original image is manipulated, augmented, and our data size becomes 2 times. So that is data augmentation. And in some cases, our data could contain a lot of noise, and that leads to overfitting. Then we can filter out some noise data and make our data quality improved. That is what better data means. Sometimes we could use transfer learning. We have nowadays big models or giant models, transformers, and clip, or a lot of data, a lot of big models. And because those giant models already have very efficient features, we could utilize those features using transfer learning. Or sometimes your model is too complicated and you need to simplify your model. And learning rate could be a problem. We're going to discuss this in more detail in the later of this course. And because you train your model too much, you can use early stopping. So you just stop training your model. Like, let's say you plan to train your model for 100 epochs. However, you are going to stop in the middle because from this point, overfitting could occur. Underfitting is quite opposite to the overfitting case. Because your model is too simple, that's why underfitting is occurring. Then you could make your model more complicated by adding more layers or units. Or you can tweak the learning rate or train longer. So in the case of overfitting, you used early stopping. But in contrast, you are going to use a longer training period. And you can use transfer learning as well here. And you can use less regularization because regularization simplifies your model. So these are some techniques to deal with underfitting and overfitting. And please take some time and try to solve this problem to check your understanding. Okay, have you solved this problem? The answer is the first option. I told you that we use stochastic gradient descent because using the whole data is not feasible. And you can refer to the previous two slides to answer this option. And in the third case, I told you that these two circles could become two lines if we use polar coordinates. And patterns, embedding, feature representation, feature vectors all refer to a similar concept. Okay, from now on, we're going to talk about linear algebra and NumPy. Data could be both structured and unstructured. In this tabular data, we say this data is structured, and image data is sometimes unstructured. And we represent data using matrices. So in this case, we have just one instance of m dimension. And if we stack n instances, then it's going to be look like this. And these two things signify the same thing, n instance features. So the first instance, second instance, and nth instance. So when we are representing data, we use matrices. And when we represent models, we use matrices as well. I showed you this slide in the beginning of this class. Therefore, you could claim that everything, almost everything, is in matrices in machine learning. So that's why we need to study linear algebra. And let's say we have image data like this, or text data, or audio sound like this. However, computers cannot understand these types of data. We need to, in some way, change this data into numbers like this. And this one is called numerical encoding. And our neural networks can learn representations using these numbers, not this raw data. And then it outputs some numbers. However, these numbers are for computers, not for humans. We need to interpret these numbers and then get some outputs. So this image represents ramen, spaghetti, and this email is not spam. And this audio sound can be transcribed this way. And the takeaway from this slide is that everything is in numbers, and those numbers are in most cases in matrices. And we sometimes call these numbers tensors. So what are scalar, vector, and matrix are? You might know that scalar is just a single number, and a vector is a collection of scalars, and matrix is a collection of vectors. So it is 2 dimension, 1 dimension, 0 dimension. And we call this rank 0 tensor, rank 1 tensor, rank 2 tensor. And we sometimes collect data, and we call this matrix as design matrix. I'm just explaining this term, so get used to this term. Okay. And an example of 3D tensor is RGB image. So we have red channel, green channel, and blue channel. And by combining these 3 channels, we have single image like this. And an example of 4D tensor is a collection of images. So we have 3 channels, W, and height, width and height of image. And if we have multiple images as a batch, then this is going to be a 4D tensor. So these are for parallel computing. So tensors are, in the context of TensorFlow, NumPy, PyTorch, they are multi-dimensional arrays: scalar, 0 dimension, vector, 1 dimension, matrix, 2D, tensors, 3D, and like 4D, 5D, 6D. Okay, so tensors are just multi-dimensional arrays. And I told you that this input data having m dimension can be dot producted with this weight, and by adding a single number bias, we get an output. We can simplify our neural network in this way. So the input is m dimensional. This one represents hidden layer. And we can collect multiple data like this, rather than just one single data. And we can process multiple data in parallel. That's why we are using these matrices. And can you spot the error on this slide? Think about it for a moment. Actually, this one is vector, and you cannot add vector with a scalar. So this should be like B, B, B. However, we're just writing this B in this way. NumPy, PyTorch, TensorFlow, and Extra handle this through something called broadcasting. So I'm going to discuss this in the implementation session. So we represent data using matrices, and we represent models using matrices as well. And that's why we need to consider linear algebra as fundamental block of machine learning and deep learning. And in this course, we're going to NumPy, which is a Python library for dealing with numerous linear algebra operations in computer or using Python. And we're going to use NumPy to implement fundamental algorithms of machine learning and deep learning. Okay, so that is the motivation of using NumPy.